Welcome back to the deep dive. We're really diving in today, tackling how energy actually moves around. It's fundamental stuff. We've got this stack of sources, physics texts, climate reports, engineering notes, pretty dense material. Our job, make sense of it all for you. So the mission is to unpack the big three: conduction, convection, and radiation. These ideas, they explain everything from, why your coffee gets cold to how our entire planet stays warm. Let's get into it.
Absolutely. We're here to sort of connect the dots, synthesize the core physics, and show you why it matters in the real world. Honestly, understanding these three, it's like a shortcut to getting your head around energy efficiency, insulation, even climate science. And before we jump in, we should mention the sources themselves. Really thorough stuff, compiled with positive contributions from physics teacher Hacı Veli Torun. Credit where it's due.
Okay, first up, conduction. This feels like the most intuitive one. Heat through touching?
That's it exactly. Direct contact. Molecules vibrating, bumping into their neighbors, passing that energy along. But here's the thing, the material itself isn't really going anywhere significant.
Right, and you see this, or rather feel this, with the classic example. Stepping barefoot onto a cold tile floor versus a wooden floor. Why does that tile feel so much colder?
Yeah.
Even if you, check with a thermometer and they're exactly the same temperature.
Yeah, that's a great one. It trips people up. The feeling isn't about the actual temperature. It's about how fast heat is leaving your foot. Tile is a great conductor. It just sucks the heat out of your foot really quickly. Wood, not so much. It's an insulator. It slows that heat transfer right down.
That's the rate of transfer. Okay, so good insulators.
Right.
What makes them good? Is it just being solid?
Not necessarily. Actually, some of the best insulators work by trapping something that isn't a good conductor. Think about fiberglass insulation or styrofoam, or even just trapped air. Air itself is a terrible conductor. Molecules are far apart, don't bump into each other efficiently. So materials that trap lots of little pockets of air, like wood or wool or, interestingly, snow, they make fantastic insulators.
Ah, snow. I remember reading that in the sources. It seems counterintuitive because snow is cold, but it insulates. How does that work?
Right. It's fascinating. When snow settles, it's full of tiny, tiny air pockets trapped between the ice crystals, loads of them. And because air is such a poor conductor, this trapped air creates this incredibly effective insulating blanket. It's why animals can survive under the snowpack when the air above is freezing. The snow keeps the ground beneath it relatively warmer.
Okay, that makes total sense. So conduction is heat transfer through touch, no bulk movement. What about when the stuff is moving, like air currents or boiling water?
Right, now you're talking convection. This is heat transfer specifically through the physical movement of fluids, so liquids or gases. It all comes down to density. When you heat a fluid, it expands, becomes less dense. And what do less dense things do?
They rise.
They rise, exactly. And the cooler, denser fluid sinks down to take its place. That movement, that circulation, is convection.
Which is why smoke goes up from a fire, or you see the water churning in a pot when it boils, or convection ovens. They circulate the hot air, right?
Perfect examples. That circulating hot air cooks food more evenly, but convection doesn't just happen in your kitchen. It happens on a massive scale. Think weather.
Okay, like how?
Let's take coastal areas, land and sea breezes. Classic convection. During the day, the land heats up much faster than the sea.
Lower specific heat capacity, right?
Precisely. So the air above the hot land gets hot, expands, becomes less dense, and it rises. This creates a sort of low-pressure zone over the land. Meanwhile, the air over the cooler sea is denser. So what does it do? It flows inland to replace the rising warm air. And that rush of air is the sea breeze you feel on a sunny afternoon at the beach.
Ah, I see. And then at night, it flips.
It flips completely. The land cools down faster than the sea. Now, the sea is relatively warmer, so the air above the sea warms up, rises, and the cooler, denser air from the land flows out towards the sea to replace it. That's your land breeze. It's a beautiful, simple engine driven by heat and density.
Okay, this is making sense. Conduction through touch, convection through flow.
Right.
But here's the big one. How does heat get from the sun to Earth? There's no touching, there's no air or water to flow through. It's just empty space, a vacuum.
Exactly. And that's the domain of the third type, radiation. Heat transfer via electromagnetic waves, like light, but also other kinds. These waves don't need any medium. They travel perfectly well through the vacuum of space. That's how the sun's energy gets to us.
Electromagnetic waves, so like radio waves, microwaves, visible light.
All part of the same family, the electromagnetic spectrum. You've got radio waves with long wavelengths, then infrared, which is what we often mean by heat radiation, then visible light, UV, X-rays, gamma rays with really short wavelengths. But here's the absolute key takeaway, maybe the most important point from all the physics sources for understanding climate and energy.
Yep.
An object's temperature dictates the kind of electromagnetic waves it mostly emits.
Oh, okay. How so?
Very hot things, like the sun's surface, we're talking thousands of degrees Celsius, like 5,000 degrees C. They radiate energy primarily as high-frequency, short-wavelength radiation. This includes visible light, which our eyes can see, and ultraviolet, UV.
Okay.
These short waves travel easily through space and our atmosphere.
Got it. Hot stuff shortwaves, like visible light.
Right. But cooler objects, like the Earth's surface after it's been warmed by the sun, or, a warm radiator in your house, or even you, they re-emit that energy too, but because they're much cooler, they emit it as lower frequency, longer wavelength radiation, specifically infrared radiation. We can't see infrared with our eyes, but we feel it as heat.
So sun sends short waves, light UV. Earth absorbs it and then sends back long waves, infrared heat. Is that the gist?
That's the fundamental exchange, yes. And this difference between shortwave and long-wave radiation, it's critical. It also explains things like why dark surfaces get hotter in the sun.
Yeah, like black asphalt or dark car seats. It gets scorching hot.
Exactly. Dark, matte surfaces are really good at absorbing incoming radiation, including that shortwave sunlight. They're also good at emitting radiation when they get hot.
And light-colored or shiny surfaces.
They do the opposite. They tend to reflect radiation. Think about wearing a white t-shirt on a sunny day versus a black one. The white shirt reflects a lot of the sunlight, so it stays cooler.
Or those shiny emergency blankets. They reflect your body heat back at you.
Precisely. It's reflecting the outgoing long-wave infrared radiation from your body. Same principle used inside a thermos flask, that shiny lining. It's there to minimize heat loss by radiation, bouncing the infrared waves back towards the hot liquid.
Okay, so let's scale this up. We have conduction, convection, and this radiation thing, especially the difference between shortwave sunlight and long-wave heat. How does this all play out for, well, the whole planet?
Yeah.
This must lead to the greenhouse effect, right?
Directly. The greenhouse effect is basically radiation physics applied to our atmosphere on a global scale. It's a fascinating balancing act. Our atmosphere is kind of amazing. It's mostly transparent to the sun's incoming shortwave radiation, the visible light, and UV gets through pretty easily.
Okay, step one, sunlight comes in, warms the ground and the oceans.
Right. Step two, the Earth, now warmed up but much cooler than the sun, radiates that energy back outwards. But as we said, it does so as long-wave infrared radiation, heat.
Got it. Then step three.
Step three is the crucial part. Certain gases in the atmosphere, mostly water vapor, H2O, and carbon dioxide, CO2. But others, too, they act like a one-way mirror. They let the shortwave sunlight in, but they are very, very good at absorbing that outgoing long-wave infrared radiation. They trap the heat, essentially. They absorb it and then re-radiate some of it back down towards the surface, keeping the planet warmer than it would otherwise be.
And that trapping effect is significant.
Hugely significant. The sources highlight this really starkly. Without this natural greenhouse effect, the average temperature on Earth's surface wouldn't be the relatively comfortable 15 to 17 degrees Celsius we have now. It would be about minus 18 degrees Celsius.
Wow. Minus 18. So life as we know it basically depends on these greenhouse gases trapping heat.
It absolutely does. It's a natural and vital process. The concern around climate change, as the sources point out, isn't about the existence of the greenhouse effect itself, but about how human activities, mainly burning fossil fuels, are rapidly increasing the concentration of those heat-trapping gases like CO2. This enhances the natural effect, leading to long-term shifts not just in temperature, but in precipitation, wind patterns, sea levels, the whole climate system.
Right. So understanding the physics helps understand the mechanism.
Mm.
Okay, let's pivot slightly. Knowing all this conduction, convection, radiation, how do we use this knowledge? How do we, control heat flow in practical ways?
Well, engineers think about this constantly. A brilliant everyday example that tackles all three types of heat transfer is the thermos flask or vacuum flask.
We mentioned the shiny lining for radiation. What else?
It combats conduction and convection using a vacuum. There's an inner wall and an outer wall, and between them they pump out almost all the air, creating a vacuum. Heat can't conduct easily across empty space. There are hardly any molecules to vibrate, and it can't convect either because there's no fluid to circulate. So the vacuum dramatically reduces heat transfer by both conduction and convection. Add the reflective surfaces minimizing radiation loss, and you've got a really effective heat barrier.
That is clever, using physics to keep my coffee hot. Okay, what about harnessing energy? Solar power comes to mind, obviously linked to radiation.
Definitely. The amount of energy arriving from the sun constantly is just immense. The sources mention the solar constant. The energy hitting the top of our atmosphere is roughly 1,400 joules every second for every square meter, or, put another way, about 1.4 kilowatts per square meter.
That's a lot of free energy raining down.
It really is.
Scary.
And that's what photovoltaic cells, PV cells, or solar panels are designed to capture. They use materials, often dark-colored silicon, that are good at absorbing the energy from specific wavelengths of incoming sunlight, that shortwave radiation. They then convert that absorbed radiation energy directly into electrical energy. The efficiency depends heavily on understanding those principles of radiation absorption.
What a journey we've been on, seriously.
No.
We went from why your feet get cold on a tile floor
Conduction.
to how coastal breezes work,
Convection.
and ended up with the electromagnetic waves from the sun that power the entire planet and regulate its temperature.
Radiation. And that core insight holds true across all scales. The difference between how hot objects radiate short, penetrating waves, and cooler objects radiate long, heat-trapping waves. Understanding that distinction, well, it unlocks so much, from designing better insulation to grasping the fundamentals of climate science.
It really does. Okay, so here's something for you, the listener, to chew on, connecting these ideas. We didn't really dig into it, but the sources mention Newton's law of cooling. Basically, it says things cool down faster when the temperature difference between the object and its surroundings is bigger. So think about putting ice cubes into a hot drink. Why does that drink seem to cool down super fast right at the beginning when the ice is fresh and the drink is hot, compared to later on when the drink is only lukewarm? What does Newton's law, combined with what we've discussed about heat transfer, tell you about that changing rate of cooling?
That's a great application question, puts the principles to work. Hopefully this whole deep dive has given you a solid foundation, a new lens maybe, for seeing how energy moves all around us.
We certainly hope so. Thank you for joining us. And again, a big thanks to the excellent source material enhanced by the contributions of physics teacher Hacı Veli Torun. We'll catch you next time on The Deep Dive.